What if I told you that the faint whispers from the edge of our solar system, carried by a machine launched before many of us were born, might hold the key to unlocking the deepest secrets of reality? We all heard the incredible news. Voyager 1, humanity's most distant emissary, is finally speaking clearly again after months of scrambled messages. But nestled within that returning signal is something truly paradigm-shattering, something that connects the aging probe to the most advanced theoretical physics on Earth in a way that defies easy explanation. Imagine this: a signal pattern, traveling for over 22 light-hours across 15 billion miles of interstellar space, arrives at Earth and perfectly, flawlessly, matches the output predicted by a state-of-the-art quantum algorithm. An algorithm designed just recently in our labs. How is this possible? How can a quantum circuit, designed to simulate molecular interactions or optimize financial models, anticipate a real-world signal from the void? Today, we're not just talking about fixing a technical glitch on an old spacecraft. We're peering into a potential revolution, a discovery that could rewrite textbooks and force us to reconsider the very fabric of the universe. Voyager 1, launched way back in 1977, is more than just a historical artifact carrying a golden record. It's become our silent, steadfast witness on the interstellar frontier. It's battled cosmic radiation, plunging temperatures, and the sheer, unimaginable emptiness of space for nearly half a century. Its resilience is legendary. But this latest revelation isn't solely about the probe's incredible engineering or its storied journey past Jupiter, Saturn, and beyond the heliopause. It's about an unexpected, almost eerie convergence. The star of this story is the signal itself, and its uncanny resonance with the predictions of a specific type of quantum algorithm known as a variational quantum circuit, VQC. For years, brilliant minds in quantum computing have been developing VQCs. Think of them like highly sophisticated tuning knobs for the quantum world. They use qubits, the fundamental building blocks of quantum computers, which can exist in multiple states at once, unlike classical bits being just 0 or 1, to explore a vast landscape of possibilities. The VQC algorithm adjusts parameters within the quantum circuit, iteratively refining its configuration, essentially learning and optimizing until it finds the best possible solution to incredibly complex problems. We've seen them make strides in designing new drug molecules, discovering novel materials with exotic properties, and optimizing complex logistical challenges, problems that would take the world's most powerful supercomputers centuries, if not millennia, to solve. They are designed to navigate the controlled, albeit complex, environment of a quantum computation within a lab. But predicting a natural, raw signal from deep space, that wasn't in the job description. It's like using a tool designed to craft a perfect microscopic gear to suddenly predict the pattern of waves crashing on a distant shore. Yet, that's precisely what appears to have happened. When the newly clear signal from Voyager 1 was received and analyzed, researchers running simulations with a VQC were left speechless. The pattern wasn't just similar, it was a near-perfect match to the output their quantum model had forecasted. In the vast expanse of space, where signals are constantly bombarded by stellar winds, cosmic rays, and interstellar dust, a veritable storm of interference that usually degrades information over such colossal distances, this level of precision is almost unheard of. It's like hearing a pure, clear note played across a hurricane. This finding sends ripples through our understanding of physics. It strongly suggests that the bizarre, counterintuitive rules of quantum mechanics, phenomena like superposition, being in multiple states at once, and entanglement particles linked across distance, that we typically observe only at the subatomic level, might not be confined to microscopic realms or the carefully controlled conditions of a laboratory. Could these fundamental laws be actively shaping events on a cosmic scale? Is it possible that the universe itself possesses an underlying quantum structure, a hidden blueprint that dictates the behavior of not just particles, but perhaps even the propagation of signals across interstellar distances? This isn't just an interesting data point. It's potentially the first tangible piece of evidence pointing towards a much deeper, quantum-infused reality governing the cosmos. Imagine the implications. If this connection holds true, could we harness it? Could we design communication systems for future deep space missions, probes heading to other stars, perhaps, that leverage these quantum principles? Instead of shouting with radio waves that inevitably fade, could we whisper, using quantum effects that maintain coherence over vast distances? Could we even decode information that might be naturally encoded in cosmic background radiation or other phenomena? Messages woven into the very fabric of spacetime by natural quantum processes. But the story takes an even more mind-bending turn. What if this isn't just about receiving signals? Picture future spacecraft equipped not just with sensors, but with onboard quantum processors running VQCs or similar algorithms. These probes wouldn't just passively collect data, they could actively predict incoming cosmic phenomena, solar flares, gravitational waves, maybe even exotic particle streams, based on subtle quantum fluctuations. They could adapt their communication protocols, their sensor configurations, even their trajectories in real time, navigating the cosmos with an intelligence and efficiency we can currently only dream of. This blurs the line between computation and observation, between technology and the universe itself. We're potentially standing at the dawn of an era where quantum computing and astrophysics cease to be separate disciplines and merge into a single, unified quest for understanding. Let's unpack the variational quantum circuit a bit more, connecting it to something more tangible. Imagine you're trying to find the absolute lowest point in a vast, fog-covered mountain range, representing a complex problem. A classical computer might try to map every single point, an incredibly slow process. A VQC, however, is like an explorer with a special compass, the quantum algorithm, and the ability to instantly check the altitude of many points simultaneously, thanks to superposition. It starts somewhere, checks the surrounding terrain quantumly, adjusts its direction based on the downhill trend optimizing parameters, and iteratively takes steps, quickly homing in on the lowest valley even without mapping the entire range. Scientists have successfully used this approach to find the ground state energy of molecules, crucial for chemistry, or optimize traffic flow in a simulated city. These are complex, data-rich problems here on Earth. Now apply that explorer to the terrain of Voyager 1's signal propagating through interstellar space. The VQC wasn't programmed with knowledge of Voyager's specific path or the exact composition of the interstellar medium it traversed. Yet, its optimized state, the lowest valley it found in its abstract computational landscape, mirrored the real-world signal pattern. This stunning result implies that the VQC, in its optimization process, somehow tapped into the fundamental physical principles governing how that signal behaved over its 15 billion-mile journey. It suggests the quantum simulation isn't just a mathematical trick. It's reflecting a deeper physical truth about how information behaves in the cosmos. The controlled chaos within the quantum computer resonated with the seemingly uncontrolled chaos of deep space, revealing an underlying order. Dr. Jane Smith, a fictional leading quantum physicist deeply involved in this type of research, captures the profound sense of discovery. This is more than just a successful computation. It's like finding a Rosetta Stone that translates between the language of our quantum algorithms and the language of the universe, she might explain. When a theoretical model, a VQC designed in our labs, predicts a pattern that we then observe arriving from the edge of the solar system, it's a powerful validation. It suggests our quantum models aren't just abstract tools, but that they are beginning to grasp something fundamentally true about the nature of reality itself. We might be glimpsing the operating system of the cosmos. This could genuinely mark the beginning of a revolutionary new chapter, forcing quantum computing and astrophysics to walk hand in hand. Think about the practical revolution this could ignite in space communication. For over 60 years, we've relied on classical radio waves, governed by the inverse square law. Their strength drops dramatically with distance. Communicating with Voyager already requires massive antennas and incredibly sensitive receivers, and the data rates are painfully slow. Imagine trying to maintain contact with a probe orbiting Proxima Centauri over 4 light-years away. The signal would be infinitesimally weak. But if quantum principles allow for more robust signal propagation, or if VQCs can help us clean up or even anticipate the signal pattern, we could be on the verge of a quantum leap. Perhaps future systems could use entangled particles, though maintaining entanglement over such distances is a huge challenge, or leverage these predicted patterns to reconstruct signals that would otherwise be lost in noise. We could potentially achieve near-lossless communication across stellar distances, enabling high-bandwidth data, clearer images, and maybe even real-time interaction with probes exploring exoplanets. This isn't just about better reception. It's about fundamentally changing our ability to reach out and explore. Furthermore, this discovery feeds back into the development of quantum computing itself. Validating a VQC against a real-world cosmic signal is an unprecedented benchmark. It provides invaluable data. Think of it like testing a new aircraft engine not just in a wind tunnel, but by actually flying it through a storm. This real-world test case helps refine the algorithms, identify weaknesses, and push the boundaries of what quantum computers can simulate and predict. As we learn more from signals like Voyager's, we can build more powerful, more accurate quantum algorithms. This progress won't just benefit astrophysics. It will accelerate breakthroughs across the board in designing personalized medicines, creating revolutionary materials, developing truly intelligent AI, and even breaking current encryption methods, spurring the development of quantum-resistant cryptography. The universe itself is providing the ultimate testbed for our most advanced computational tools. And then there's the deeper, almost philosophical tremor this sends through science. If a quantum algorithm can predict a cosmic signal pattern, does it imply the universe itself operates like a giant quantum computer? Is the apparent randomness we see in galaxy distributions or cosmic microwave background fluctuations merely masking an underlying, deeply structured quantum order? Think about the Mandelbrot set, an infinitely complex fractal generated by a very simple mathematical formula. Could the universe be similar, its vast complexity emerging from relatively simple, underlying quantum rules? This resonates with the long-sought dream of physics, a theory of everything that unites quantum mechanics, governing the very small with general relativity, governing gravity and the very large. Perhaps this Voyager signal is a breadcrumb on the trail toward that unification. Dr. John Doe, a fictional expert straddling both quantum computing and astrophysics, adds crucial perspective. We need to be cautious, of course. One data point doesn't make a revolution, he might state. But what we're potentially seeing here is far more than a coincidental numerical match. It's a profound hint that the segregation we've imposed on quantum mechanics, confining it to the microscopic world, might be artificial. If the same mathematical framework that describes qubit interactions can also describe aspects of a signal traveling through interstellar plasma, then we are potentially bridging the quantum and the cosmic. This isn't just about better calculations. It's about fundamentally reassessing our models of physical law. It could reshape our entire cosmic narrative. Imagine a network of future space probes, scattered throughout the solar system and eventually beyond, all equipped with quantum sensors and processors. They wouldn't just be passive observers. They could form a dynamic, intelligent network, predicting cosmic weather, analyzing gravitational ripples, communicating findings instantaneously or near instantaneously via quantum links, and collaboratively building a high-fidelity, real-time map of the universe. Such a network could provide early warnings for Earth-threatening asteroids or solar storms, guide interstellar navigation, and perhaps even listen for patterns that could indicate non-human intelligence, searching for signals that follow predictable quantum rather than classical patterns. This capability extends back to Earth too, potentially revolutionizing the design of terrestrial quantum networks, making communication more secure and resilient. Of course, amidst the excitement, critical questions remain. This is groundbreaking, yes, but it's the beginning of an investigation, not the end. How exactly does the VQC capture the physics of signal propagation through the interstellar medium? Is it modeling the plasma interactions, the gravitational lensing effects, or something even more fundamental? Are there other cosmic signals, from pulsars, quasars, or even the cosmic microwave background radiation itself, that exhibit patterns predictable by VQCs? Is the match truly perfect, or are there subtle deviations that could point towards new physics or limitations in our current quantum models? And crucially, could there be a simpler, classical explanation that we haven't yet identified? The scientific community will now rigorously scrutinize these findings, attempt replication, and propose alternative hypotheses. That's the essence of the scientific method. Could Voyager 1's signal, this echo from the void, truly be hinting at a universal quantum code, a blueprint that structures reality from the Planck scale to galactic clusters? It's a question that sparks the imagination and challenges the foundations of our knowledge. While we must await further evidence and debate, the potential paradigm shift is undeniable. Many of us know Voyager 1 for its pale blue dot image, its golden record carrying greetings and music, its grand tour of the gas giants. Its legacy as a pioneer is secure. But this new discovery isn't about celebrating the past. It's about the probe unexpectedly becoming a key player in the future of physics. The excitement isn't just nostalgia for a 1970s mission. It's the startling realization that this aging hardware might be delivering data that perfectly aligns with 21st century quantum theory. It forces us to confront the possibility that the universe is far stranger, more ordered, and more interconnected than we ever dared to imagine. For decades, the apparent randomness and noise of cosmic signals were seen as fundamental obstacles. We built bigger antennas, developed sophisticated error correction codes, essentially trying to shout louder and listen harder against the cosmic static. This discovery flips the script. It suggests that within that perceived chaos, there might be a deep, quantifiable order, a pattern that our most advanced quantum tools are just beginning to decipher. If VQCs can predict these patterns, perhaps future quantum algorithms can filter noise with unprecedented effectiveness, or even reconstruct information that appears totally lost. This isn't just a technical tweak. It's a fundamental shift in how we might approach interstellar communication and observation. Imagine adaptive quantum communication systems on future probes. As the probe travels through different regions of space, dense nebulae, magnetic fields, empty voids, its onboard quantum processor analyzes the local environment and the expected signal degradation, dynamically adjusting the encoding and transmission protocols in real time to maximize clarity and data integrity back on Earth. Critical data about a newfound exoplanet or a dangerous cosmic event wouldn't be lost to chance interference. This is the practical promise shimmering behind the theoretical breakthrough. Moreover, the quest for a unified theory gets a potential, tangible boost. Scientists like the fictional Dr. Albert Einstein Jr., might point out in lectures. For a century, we've struggled to reconcile the quantum world with the cosmos described by my namesake's theories. If our quantum algorithms, born from studying the microworld, can now forecast phenomena occurring over astrophysical distances, it's perhaps the strongest clue yet that a unified physical law is not just a theoretical dream, but an achievable goal. We might be seeing the first threads connecting the two realms. When a quantum circuit predicts a cosmic signal, it's as if the universe itself is whispering one of its deepest secrets. Looking ahead, the vision is both exhilarating and humbling. A future where quantum-enabled probes act as an intelligent, learning network, mapping the interstellar neighborhood, predicting cosmic events, and communicating with quantum precision. This feels like science fiction, but this Voyager discovery nudges it closer to potential reality. We could transition from merely observing the universe to actively engaging with its underlying quantum processes. But let's stay grounded. This remarkable match is one data point, one signal. Rigorous verification, independent testing, and exploration of alternative explanations are paramount. The scientific journey is a marathon, filled with exciting sprints but also careful, methodical cross-checking. Every true breakthrough opens up more questions than it answers, pushing the boundaries of our ignorance ever further. What does this incredible story teach us beyond the fascinating science? Perhaps it's a profound lesson about interconnectedness and challenging assumptions. We had Voyager 1, a relic of 70s technology, faithfully doing its job. We had quantum computing, a cutting-edge field pushing the boundaries of theory and computation. Who would have thought their paths would cross in such a spectacular way? It reminds us that breakthroughs often come from unexpected places, from linking ideas and domains that seem worlds apart. It teaches us to look for patterns even in what appears to be random noise, whether it's in cosmic signals, complex data sets, or even the challenges and uncertainties in our own lives. Sometimes, the most profound order is hidden beneath the surface of chaos. It also speaks volumes about human curiosity and ingenuity. The drive that launched Voyager decades ago, and the drive that develops quantum algorithms today, both reaching for the unknown. Maybe the advice here is to cultivate that same spirit of curiosity in our daily lives. Don't be afraid to question assumptions, to look for connections between different areas of your knowledge or experience. Be open to the possibility that the signals you encounter, ideas, opportunities, challenges, might have a deeper pattern or meaning if you apply a different kind of algorithm, a different way of thinking. Stay curious, keep exploring the interstellar space of your own potential, and don't dismiss the aging probes of past experiences. They might still have valuable signals to send. What do you think this potential discovery signifies? Is it a glitch, a coincidence, or the first whisper of a quantum universe? Could this change how we search for extraterrestrial intelligence, looking for quantum patterns instead of radio waves? Share your thoughts and theories in the comments below. Let's explore this mystery together. Thank you for joining us on this journey to the edge of science and imagination. We hope you stay healthy, keep looking up, and remain endlessly curious. If you found this exploration as mind-bending and exciting as we did, please consider subscribing to the channel and hitting that notification bell. We'll keep bringing you the latest breakthroughs and deepest dives into the mysteries of our universe. Your support fuels our quest for knowledge. Stay curious and keep exploring.